Hey, welcome back. In this video, we're going to talk about exponential functions. Specifically, we're going to build the basic idea of an exponential function, look at the structure, then look at the graphical representations of exponential functions. All right, in order to acquaint ourselves with exponential functions and their basic structure, I want us to consider a situation comparing two types of growth. So in this situation right here, we're going to have 100 people initially know about our rumor. And then what we're going to do is look what happens as this rumor spreads, but in two different ways. In the first situation, we're going to consider starting with 100 people, then every hour, 500 more people hear about the rumor. And in the second situation, we're going to consider the situation where the number of people who know the rumor doubles every hour. Importantly to our conversation, this situation here where 500 more people are learning about the rumor each hour is called linear growth. It's an additive growth. And in this situation right here where the number of people is doubling each hour is a multiplicative growth, which we call exponential. And at this point, we've actually seen a lot of different types of behavior of functions. But importantly to me, I think the idea of linear functions really lines up well with exponential functions. So let's talk about the additive situation here, the linear growth first. We feel really comfortable with this, and this will be obvious or probably pretty clear, but I want to use it again to describe the similarities with the exponential growth. So if here we write a table of values for the first 5 hours. So at time 0, we have 100, and then each step here is a difference of 500. Each hour, the number of people who know of the rumor is growing by 500. Importantly for how I want to generalize this statement is the 600 here. I'm going to think of the original 100 people plus 500 been added one time for that 1 hour. And after 2 hours, yes, I'm up to 1100, but also I'm going to think about that as 100 in the 100 original folks plus 500 twice. And that same pattern continues on. Every hour I'm adding a new 100. Beautifully though, if we have this repeated addition of 500, we can use multiplication to describe that. So in this case right here, I'd write that as 100 plus 500 3 times, or 500 times 3 takes care of that. And we have that same pattern all the way down. In this case, it's 500 times 4. And finally, in hour 5, it's the original 100, and then we're gonna have added 500 5 different times. And then to move the conversation of what happens in hour t, again, this is really clear. We feel pretty comfortable with linear growth. We have this additive growth. We could describe this, we'll call it r of t. For the rumor function, this is 100 plus 500 times t. And again, the multiplication is used here not because multiplication is a step each time, but because multiplication describes this repeated addition where we have an initial amount of 100, and this is the how much we've added each time, multiple times, well, t times specifically. So then if we do exactly the same analysis with this case where we double and we create a table of values, we know again we start at time 0, we start at 100, exactly the same, and then we double. Importantly, a big difference here is that when I look at this table as we go up by an hour, the difference between each of these obviously changes as far as additive. So there's a difference of 100 here, but between hour 1 and 2, it's a difference of 200, then a difference of 400. And importantly, that's one way you can identify the difference between linear growth and exponential growth. Linear growth will always have the same difference between each step as long as you're making the same equal steps over here. So we're going up by an hour as we go down this table, so we go up by exactly 500. In this case, since we don't have this similar additive difference between each step, we know it's not linear. So what I want to do is analyze this in exactly the same way I did with this linear situation over here. So again, we start at time 0 with 100 people who know, and then we double. So what I want to think about this is the original 100 people times 2, which is equal to 200. And then when I step down to the second area, I now do another multiplication by 2, but I'm going to think about that as this original 100 times 2 twice. And what you can see is we have very similar pattern that we had over here, but instead of repeated addition that we turned into multiplication, in this case, and now I'll show you for this third example, we have repeated multiplication, which we represent by exponents. So this would, in this case right here, I would think of this as 100 times 2 3 times, or 2 to the third power, because again, repeated multiplication is denoted by exponents, repeated addition is denoted by multiplication. And then continuing this trend here, in hour 4, we would have 100 and have multiplied by 2 4 times in hour 4. And then for hour 5, we would have 100 times 2 to the 5th. And so again, we have this very similar structure. We have this initial amount, but again, instead of using multiplication here to denote the repeated multiplication in this case, we use these exponents. So if we want to represent this rumor as a function of time in this situation right here, or the number of folks who know the rumor, we would have 100 times 2 to the t. And this is where I think these are beautiful examples to show together, where most people are grounded in the idea of linear, is that we have this initial amount of 100 that shows up in both of them. So in this case right here, this 100 on the front here is the initial amount. And then the major difference here is this operation happening in between, and then us representing that operation happening multiple times, right? So in this case, I'm using multiplication, I was using addition, and instead of using multiplication to denote repeated addition, like I previously said, we're using an exponent to denote repeated multiplication. And so in this case right here, this factor of 2 does not mean I'm adding a certain number of times, but this means doubling per hour. And finally, we can't finish this scenario without talking about which one's better, or which one has the more people know the rumor. And it should be clear when you see this, that while adding 500 each hour initially makes this situation the one that where more people will know of the rumor, in this case, it doesn't take too long before this greatly surpasses this. So for instance, between hour 0 and 1, we have an addition of 200. Between hour 4 and 5, we're adding 1,600 more people. And clearly then by these table of values, you can see that in this situation right here, if we continued, this situation where we're doubling would be a lot more people. And now you may be thinking, well, yeah, but that's doubling. What if it wasn't growing that fast? Well, actually, in the scenario where we have exponential growth, not decay, and we'll talk about that in a second. If we have exponential growth, it will just take a matter of time before this surpasses this situation. And just to drive this home real fast, what I want to do is look at a graphical representation of both these situations. So in orange here, we have this linear situation, which you're expecting. We have identified this point at 0, 100. That's this initial condition, this initial state at 0 hours. And then we have this nice slope, or this nice straight line. And that comes from the fact that we're adding exactly the same thing every hour. It has this same slope, that every hour we're going up 500. And then looking at the green graph, which is the exponential graph, we see that it starts at exactly that same point at 0, 100, as in the linear situation right here. And then the growth is slower. So for these first few hours here, we have the green function, the exponential function, is lower than the linear function that's growing at a steady rate, but it doesn't take much time at all. Specifically between hour 4 and 5, the situation where we're doubling each hour far surpasses and continues to grow much faster than the linear situation. All right, so before we move on, let's just generalize the idea of an exponential function. So we say an exponential growth or decay function is a function that grows or shrinks at a constant rate, or by a constant factor. And the most important thing to this conversation is this idea of a constant factor that we've discussed before. And the general form for an exponential function is f of x equals a times b to the x. And we know what role these play right here, as we saw in the previous example. So a in this case is the starting or initial amount. So a is the initial amount, or more importantly, it's the amount you have when your x value is 0, or at time 0, whatever 0 represents. B is the growth or decay factor. In the previous example, that B value was 2. So B is the growth, decay factor. And importantly to our discussion of exponential functions, b is strictly positive. So we're not going to accept negative numbers of b. And that's important because there's a lot of different issues. If we had this number that's being raised to this variable exponent here, and if we had allowed negatives, it would act very strangely, and there would be issues if we had fractional exponents of taking the square roots of negatives. So b must be exclusively positive, and also b cannot be equal to 1. If b is equal to 1, then this factor right here always outputs 1, and this isn't an exponential, it's actually a constant function. And before we move on to any other examples, I want to just talk quickly about this idea of exponential growth versus exponential decay. In the first example that we saw an exponential growth function. If I rewrite this as f of x equals 100 times 2 to the x, importantly, this is growth or an increasing, strictly increasing function. As we increase the independent variable x in this case, this gets better by a factor of 2 for every one that we increase right here. So we have, this is importantly, exponential growth. If we instead had a function like this, where we had f of x equals, let's say, 128 times 1/2 to the x, in this case right here, every step or for every one we increase our independent variable here, this actually is applying a factor of 1/2, which will take half of what we had before, meaning this function will be strictly decreasing by 1/2 each time, and we would call this exponential decay. And the beauty is it's not hard to identify whether we have exponential growth or decay. It's all about this exponential factor right here. So in this case, we have exponential growth anytime that b value, which is this exponential factor right here, is greater than 1. That means we're going to get at least a little bit bigger. If we're even just a little bit over 1, a little bit bigger than the time before. But if our factor is something like this, between 0 and 1, we will have an exponential decay model.